So you've definitely seen this before, the assumptions of linear regression. One, the relationships need to be linear. Two, the estimated error for each unit residuals are normally distributed, homoscedasticity. The residual errors are not related to any other variable. In other words, if there is error, the error itself is not actually correlated with other variables that you've measured. In other words, that error should be random. That the observations between the units are independent. In other words, units within your original study are not necessarily directly impacting the performance or the scores of other people in your study. The variance itself is homoscedastic. The outliers are not present. The predictor variable is fixed and not random. So what that basically means is that whatever you're trying to predict, the predictor needs to actually be a fixed scale, not some random number. And finally, the variables themselves, however you're measuring both of these continuous variables, they are reliable measures of a consistent behavior, attitude, or psychological construct. What we're going to talk about now is some more unique things that you need to think about that could also cause problems in your regression. And what I mean by problems is not necessarily that it would affect whether or not you find a significant relationship. It's about whether or not you can trust the numbers that are coming out of that equation. So the assumptions that we just listed are supposed to make it less likely that there's a problem. That as long as your relationships are linear, there is no, the residual errors aren't related, our observations are independent, our variance is homoscedastic, there's no outliers. The predictors themselves are actually measuring psychological constructs in a reliable way. Generally speaking, we can trust those results. But there are some situations that would not be captured by these assumptions that we also need to be at least aware of and look for. Before we talk about those, just again a brief review of why we use correlations and regressions. So we can use correlation and regression as we can any statistical technique to do theory verification. So we can basically predict a significant correlation between two variables to basically further science. We're looking for new relationships. We're looking for new predictors on new outcomes. Now, that's simply verifying theory or past research, and that's kind of pure research. Once we have that, we could also then be adding that step of prediction, that once we know this and we know this relationship, we can now use that relationship to predict people's future behavior based on a predictor variable that's related to that outcome. We can also then look at validity. So higher correlations between new and older psychological measures indicate that they are measuring the same construct. So we can use correlation regression to verify new measures based on their relationship to pre-existing constructs or old measures. And again, we can use that same correlation regression to look for low correlations between unrelated constructs. So a lot of times when we're trying to validate a new scale, in other words, we want to show that a new scale is a valid measure of a construct, what we'll do is use correlation and regression to find out, is it related to things we'd expect it to be highly related to, and is it not related to things that we don't expect it to be related to? That argues for its validity. And finally, we can also use correlation and regression simply to measure reliability. So the same individual should produce similar results across multiple observations if what we're truly measuring is a stable construct. And correlations between multiple observations of the same measure indicate that reliability. So just kind of keep in mind that the reason that we really are spending so much time on correlation and regression is not only their ability to give us prediction, which has a very strong practical application, but also correlation and regression are kind of the cornerstones that we use to look for validity and reliability in psychological measures. So there's a lot that we use these methods for. Now, I talked about other things we need to be concerned above and beyond the assumptions, and this is influences on the correlation coefficient. And these include restriction of range, the use of extreme groups, combining groups, outliers, curvilinear relationships, and then finally a discussion of sample size. So let's start with restriction of range. All of these are basically problems that can show up in your correlation that will not show up numerically. They will not show up as you test the assumptions. You really have to be aware of them more methodologically. So I'm really not sure why I have these two cartoon images here. They're fairly dated at this point. If you actually know where these two things come from, consider yourself a student of pop history. But both of them represented monsters that you didn't want around. So basically, they're kind of like gremlins, that would throw a wrench in the works. And that's what these are, is wrenches in the works that aren't necessarily being caught by our first pass of just asking, are the assumptions met? So what restriction of range refers to is this is a methodological problem. So for instance, if we know that there's a fairly strong relationship between SAT scores and GPA, and there is, it's a solid predictive relationship. In order to really trust that relationship, though, we have to have a large range of SAT scores and a large range of GPA scores. In other words, that predictive relationship is based on an open range, if you will. From the very lowest SAT score to the very highest SAT score, from the very lowest GPA to the very highest GPA. Now what happens is if that we actually have a prediction equation based on a non-restricted sample, it may not work as well in a restricted sample. So think about the fact if we actually looked at only SAT scores of 110 or higher. So we're looking at the top third of the distribution. And we have no one with a score less than 110 in our sample. If we would then use that first sample of A to try to predict scores in that second sample of B, the one with a restricted range, what we'd probably find is that the relationship there is not as strong. There is more variance at that point. Now, this doesn't necessarily mean a shotgun or homoscedasticity or heteroscedasticity. What this simply means is that if we are actually looking at any smaller n of a larger sample, and we're only looking at a restricted range of very high scores, only medium scores, or only low scores, we probably need to actually run an additional regression to find out what is the actual predictive quality of the two variables we're interested in this particular sample. We cannot generalize a prediction equation that looked at everyone's scores from the very lowest to the very highest to a restricted range sample and be able to trust that data. So this is, again, it's not something that's going to show up necessarily in a statistical analysis. It may not even show up in a test of heteroscedasticity or homoscedasticity, but it is something that we methodologically want to be aware of. If we use extreme groups, so instead of just restricting range to one group, we look at a couple of extreme groups. We're usually going to find actually that we have better prediction, or at least the appearance of better prediction, because again, think about a good regression. A good regression is usually an oval shape, and there's less error at the top and less error at the bottom, and there's less participants at the top and bottom. So if we actually have an initial predictive equation that only included people that were very low or very high, and we didn't actually have anyone in the middle, that regression equation would be stronger than what we'd find in an overall sample that included all of those people that run in the middle. And this can go both ways. So if you've got an additional sample, let's say in this case B, you've got the sample that has everyone in it. You run your regression, you create your regression equation, and you start using it for prediction. But in the sample that you're predicting, there's almost no one that has a medium score on need for achievement. It's either people with very high or very low need for achievement. You would actually be under-predicting in that case. Likewise, if your initial sample was A, and you created your regression prediction equation based on this sample with no one in the middle, but then you started using that regression equation to predict people that actually run the gambit from low to medium to high, you would find that you actually have a lot more error than you thought you did, because a lot of people in the middle were not including your original sample. So both of these are examples of basically that if you are truly trusting a regression equation to predict behavior in a future sample, methodologically, you need to make sure that your initial sample group that you created that regression equation on, the sample group that you had access to both scores, is relatively similar to the sample that you're actually predicting. This happens a lot in organizational psychology, because a lot of times what we end up doing is we actually test our predictors in a large sample of people that already have the job, that very well may include people that the predicting set would have said don't hire. So we have a large sample of a large variance in our initial sample. But then we start using our predictor to only hire people with high scores. And we often find what's called validity shrinkage. In other words, it is less predictive of performance than we thought it was, based on the fact that that second sample is now a restricted or range sample. It's only people that scored high, even though the prediction we used was from a sample that included all of our groups, people that scored low, medium, and high. So this really is just kind of a thought exercise of you need to ask yourself, if I'm trusting a regression prediction in a clinical setting, in other words, it's an applied setting, you're making choices based on it. You want to make sure that your sample group, the group that you created your prediction equation on, is substantially similar to the group you're actually going to be analyzing to predict with or to predict for. We also want to be very careful about combining groups. And generally what happens here is that there's a third variable that we really haven't accounted for. So for example, if we actually divided, so I'm going to look at the very first example at the top left. Let's say that this represents two groups of people, men and women. And we actually look at men and we find out that men tend to be higher on Y and X, whatever that is that we're measuring, than women. But it's not actually related. And women tend to be lower on Y and lower on X than men. But again, they're not really related. If we then had both groups in our study, so we basically didn't actually divide them out, we just had men and women, we would probably find a strong relationship, because we're combining two groups, both of which who had zero correlations. Now we can also find that if those two groups, for example, if men scored, so we're now in the middle top, if men scored in general higher on Y and a little lower on X, but it was related, and women, excuse me, scored lower on Y but higher on X, but it was related, again, if we had both men and women on our sample, it would probably show up as no relationship. We can also get situations where one group has a positive relationship, the other group gets a negative relationship, and that's shown on the example at the top right. In this case, we'd actually find that we probably violated homoscedasticity. And there's a lot of different situations that we can find this happening in. This generally means that if you run a correlation, it's up to you theoretically to ask, would I expect there to be gender differences? Would I expect there to be ethnicity differences? Would I expect there to be underclassmen versus upperclassmen differences? And if I have those variables, I want to look for this. Because if I don't find a relationship, this might be why I didn't find a relationship. If I did find a relationship, I probably want to make sure that relationship is present in any of my subgroups before I definitively state I found that relationship. And if I actually find homoscedasticity has been violated, in other words, I've got that shotgun pattern, I may again want to divide out my data set by various other variables that I might have, gender, ethnicity, age, etc., and see, is that actually interacting with my variables in a way that's creating that problem? Now, there is no way to know this for sure, other than just running a lot of individual correlations and breaking up your data set to look around. But if you were really expecting a relationship and didn't find it, this is one of the tools you can do to find out what actually is happening and maybe get an answer. If you violated homoscedasticity, this is a potential way you could look to say, this is what's happening. I actually have a difference in ages. At certain ages, that's a negative relationship, and other ages, it's a positive relationship. Putting those two together would give me that shotgun pattern. Or if you find a relationship when you really didn't expect one, then you may want to look at, is there some gender differences? Is there group differences? Is there some other variable I can look at that might explain why that happened? And again, that's shown in the upper left corner. Just a reminder that if you do have outliers, you may not violate the assumption of an outlier. A lot of times an outlier may end up being what's called a multivariate outlier. What that means is the example to the right, that little guy up there, or girl, so pretty moderate on Y, very low on X. We might actually find that their score on X is not more than 3 standard deviations away from the middle. We might find their score on Y is not 3 standard deviations away from the middle. So it's not an outlier on Y or X. But when we look at the scatter plot, it's a multivariate outlier. The combination of how far of an almost outlier it was in Y and almost an outlier in X makes it clearly a problem in our analysis. And the problem with a multivariate outlier is it will often slip through the cracks of us just testing for normalcy in our continuous variables, but it will strongly affect our outcome. So notice that if I actually bring over this correlation without the outlier, Notice how the correlation line changed with that one present. So that one variable is completely changing our prediction because the line is being moved to try to account for the error of that outlier. And again, this would be a case where there's really no easy way to look for multivariate outliers other than looking at scatter plots. So if you saw a dot sitting out there, the thing we would check for then is how far away was it from the mean on our various predictors? And we might decide, again, this is a theoretical decision, this is a methodological decision, to make the argument of why we remove that outlier to make a better predictive model. And finally, remember that with curvilinear relationships, we need to actually look for them, especially if we see them in various scatter plots. And again, if we actually have a correlation for nonlinear relationships, there's two things we can do. We can use multiple regression to put in a curvilinear model, or if it's a curvilinear model, if it's a curvilinear relationship, but we're not wanting to use multiple regression, it's a simple regression between two variables, we can also convert that data into ordinal data and run a Spearman's test instead. And again, this is something that we often have to look at those scatter plots to determine what's actually going on. Because not always are we actually going to get the violation of a linear relationship simply by a scatter plot. Sometimes a linear relationship is the better fit even if it does look curved. Other times it isn't. It requires us to do a little more digging. And the final thing I want to remind you about is that the lower the sample size, the correlation becomes a lot less reliable, and that's why with a small n, generally speaking, it's a lot harder to find a significant relationship, because again, significance is how likely is that to happen due to chance. So for instance, this is an example of with a population with an n of 40 on the far left there, we see an R of 0.48, which would be actually significant with an n of 40. But if we randomly took a sample of 20 of those participants into sample 1 and a random sample into number 2, so this is taking those 40 people, splitting them randomly into a group 1 and a group 2 of 20 each, one of those groups we'd find an R of 0.18, and the other group we'd find an R of 0.62. That's an indication of as you get to lower sample sizes, it's a little harder to trust the R you're getting at. Putting them together, we're probably closer to the truth, R of 0.48. But if I only had a sample of 20, again from this same group of 40, and I happened to have that sample number 1, I would conclude no relationship. If I randomly had that sample number 2 of 20, I would actually decide that it was a stronger relationship than it actually was. So generally speaking, what this tells us is that when we're looking at sample size, low n sample sizes, the correlations tend to be unreliable. Individual participants have too much leverage over the correlation, either in a positive or negative way. So when we have a small n, a large relationship can be non-significant, but also an almost non-existent relationship might actually be indicated as being significant. So generally speaking, we want to avoid a small n. When we're running correlations, we want the largest n we can possibly get. The larger the n, the more that we can trust that results. Now there is a downside, and that is that very small relationships can be found significant with a large n. That doesn't mean they're not significant. That doesn't mean it's not a significant pattern. It just means that you need to recognize that as you get to a larger and larger n, significance is less and less important. It's more of just a marker that it is indeed a very likely pattern. Now you have to ask, how strong is that pattern? Is it really a meaningful pattern? It may be a very small relationship that's not really very good for prediction at all, but still significant with a large n. But we can trust it more. It's probably going to be that if we took sample after sample after sample, we would find similar numbers over and over again of that relationship. And the lesson here is that when all else fails, we want big N, not small n. So anyway, broadly speaking, just some additional warnings. Correlations, again, do not address issues of causation. So correlation does not equal causation, but correlation can address causation if it is methodologically designed to do so. Remember that correlation is a statistical technique, just like t-test, just like ANOVA, just like multiple regression. Causation is a methodological issue. Do you have a statistical relationship? Did the cause precede the effect in the study? And are there no other logical explanations? Remember that correlation is suspect with a low n, and the lower the n, the more suspect it is. The higher the n, the more trustable it is. Correlation is not a way to establish the independence of predictors. In other words, if you're actually looking at the interrelationship between correlations, you need to move to mediation within a multiple regression. Also, correlation is a relatively poor inferential statistic. So remember that inferential statistics is inferring to a larger sample. So from your sample to a larger population. Correlation tends to be a weak predictor of statistical significance at small n's and a very sensitive, almost too sensitive predictor at high n's. And also, what is a strong, moderate, and weak relationship is somewhat up for interpretation whenever we're talking about correlations, because the correlation is used in so many fields with different markers. What might be considered a very weak relationship in one field might be an enormous advantage in another. For example, if I can predict 10% of your productivity in an organization over the next 20 years with a predictor, that might be the equivalent of millions of dollars saved. While if I'm trying to predict 10% of your reading ability, that might be a relatively small factor compared to things I could be using to predict that same ability. So it really is a relative statistic. How much is it predicting, and is there better predictors out there I could be using?